Thank you very much, Shira. All the thanks is for you to invite me here and to work here in Manaus together with Chris and Ora. Actually, you'll hear the name Chris quite a few times in this talk because our lives tend to cross paths. Actually, here, this is a picture when I was doing my postdoc in Chris's lab at McMaster. Still a bit younger, you might know this guy as well. Martin Grossel has been here as well. And we went fishing behind the university, and as always it ended up being competitive of who has the biggest one. And of course, you know, women are better at everything, so yeah. Anyway, here you see Chris visiting us with Makiko. And yeah, some of my former PhD and master students. I studied at two different universities, at the University of Hasselt and Leuven, and I did a postdoc at McMaster, as I just mentioned, with Chris. Our university is in Antwerp. Antwerp is a harbor city. Not exactly near the ocean, but in an estuary of the River Scheldt, and our university is divided over 4 different campuses in the city. So the old city center with the most classic buildings, where the university started as a trade school 150 years ago, and then going from slightly more modern to more modern out campuses, which are already like 35, 40 years old as well. So, for those who are not familiar with Belgium, we are here kind of in the middle of Europe and the European Union, and Belgium is one of the countries that was there with the Union from the start. This is our flag, and actually we are one country, but we also have different regions. We speak 3 different languages in Belgium, and there are 3 different partly independent regions, which is Flanders, where I'm from, and where we speak Dutch, and Wallonia, where they speak French. This is the bottom part, so the more southern part, which is the least densely populated and also the most forested area. And then, because in Brussels they both speak Dutch and French, they didn't know where to put that, so it got their own independent region. So overall, the size of Belgium is 30,000 square kilometers. I looked it up. Manaus microregion region is bigger. So it's a small country. The highest elevation is less than 700 meters, so it's close to the coast, so relatively flat. We only have this little bit of coastline here, so 66 kilometers or 67 kilometers. Nevertheless, we have more than 11.5 million inhabitants, so we are one of the most densely populated countries in the world. So 60% of those live on 40% of the surface in the region in Flanders, where I live. So 3 official languages, we have 6 governments.
Wow.
Yeah, because 1 federal and then 1 for each of those regions, and then 1 per language, and German is the 3rd language, so yeah, it gets complicated. But I guess Brussels is the best known because it has the headquarters of the European Union and of NATO. I guess politicians don't mind them being in Brussels because it's not a very powerful country that could struggle with other countries. If it's in France, then the UK or Germany will say, hey, but Belgium, you know. Okay, the average temperature is 11 degrees Celsius.
That's a nice place to be.
Yeah, sometimes, but you see the maximum can be over 30 and these last years even over 35. In Belgium we have officially a heat wave if it is more than 30 degrees Celsius 3 days in a row. So that tells you something about how little that happens when it's officially called a heat wave. Some fun facts about Belgium. We produce 800 different kinds of beers. So we like our beers. The average consumption is 150 liters of beer per person per year. The chocolate pralines are invented in Belgium and are one of the specialities. So we also produce lots of chocolate. We always think that we invited chips. We hate to call them French fries in English. In Belgium, in Flemish, it's just Belgische frieten. And they usually come together with beef stew or mussels as our national dish. A kind of a fun fact to know is for a very long time there were no McDonald's in Belgium because we had our own chain of burger restaurants. And then they tried to invade Belgium and we were the only country where they ran at a loss. And then they could do two things, either retreat or over-invade, and they chose the second option, so now they are well present, but still lower than other countries. And we were the first country to legalize euthanasia and gay marriage, or second for gay marriage. So, here we are. This is the Wallonian part, and this is the Flemish part, with Brussels here in the middle. The good thing about living in a small country is that everything is within reach. If you put a circle of 50 kilometers in diameter around, well, so this is 50, so 25, in any direction from Brussels, and you already cover a large part of the country. Make that 50 in any direction, so 100 across, and you're abroad, basically. Our research group at the University of Antwerp is called Systemic Physiological and Ecotoxicological Research, but because that is a whole mouthful, we call it SPHERE. And we are mostly about ecotoxicology, as you can see, looking at how harmful substances are, but also what the mechanisms are behind these damages that they do. And we like to do that over different levels of organization, where we go from the molecular, which is the fastest to measure and the first response, but ecologically maybe the least relevant, all the way over tissues and organisms to populations and whole ecosystems. So there's also field biologists in our research group. And you can see here people in action wearing thick coats and gloves, because it can be cold if you work in the water. However, I also like to, besides the toxicological part, work on more natural stressors. Oh man, I forgot to press start on my timer. So I'd like to go and explore extreme environments. And this is a picture from 2007 when we stayed here. And also together with Chris again, we went to Kenya, where we have very high pH alkaline lakes. Here you see a soda crust on top of the lake, which is kind of the opposite of what we have here, acidic and very soft water. But my favorite place I discovered during my postdoc is Banfield Research Center Marine Research Center on Vancouver Island. This is the view from the lab. I mean, what more can you want, right? Where we usually work with dogfish, spiny dogfish. We had some small European dogfish at home as well. and other people work with hagfish there. So, as a researcher, but also as a woman and a mother, it's not always easy to travel around the world, so you just have to take them with you. Sam here trying to catch a shark, Robba grabbing a beer. I assure you I was taking that away, not giving that to him. But he had the true spirit of the fisherman from the start, let's say. Sam actually managed to catch a shark that day, and I later had to come to kindergarten to explain that she really wasn't lying, and I could prove it with pictures that she caught a shark. So, very tough fisherman, or maybe not so tough, because after about an hour they kind of went from beer to back to their bottle. They look a bit different now. They grew up. So the talk, the science part. I would like to talk today about ammonia. This is one of the things we have been working on. Chris might have given his talk here, the good, the bad, and the ugly, I think it was, about ammonia, where he also found that although we all know that ammonia is toxic at high concentrations, it can be beneficial at very low concentration and even improve growth. The two extra names here are from former PhD students. Amit finished his PhD quite a while ago and was also a postdoc in my lab, and he's now a professor at the University of Arkansas in the United States. And Yatsna just defended her thesis last September, so very recent, and she happens to be his wife. So this is the first picture I saw of them together. After the marriage, she came to Belgium, and 3 weeks later she was at my door saying, "I'm really bored at home, can I not be a volunteer in your lab?" And one came after the other, and she started doing a PhD. This is what they look like in real life. Okay, so ammonia. Ammonia in the environment can have different sources, and certainly in densely populated areas, as the one where I live, it could mainly be from sewage effluents, but also a lot from agriculture, and more specifically from the meat industry. We have a lot of pig industry, and they actually produce a lot of manure that seeps into the soil and comes into the water. In aquaculture circumstances, it could be from uneaten food, but of course also from the metabolism from the fish themselves. So it appears as ionized and unionized, ionized ammonium and unionized ammonia, which depends on the pH, but under physiological conditions, most of it will be ammonium. This is the less toxic form because it does not penetrate membranes that easily as a charged ion, but the toxicity comes mostly from the unionized ammonia. In the rest of the talk, I'll talk about ammonia as a whole, as total ammonia. So, as said, it is not only common in the environment, but it's also important in the global nitrogen cycle, and is an important nutrient for plants and algae. In aquaculture, it can play a negative role if concentrations get too high and impair growth. So there are water quality guidelines for ammonia to try to protect aquatic animals against ammonia. If we look at levels that can occur in nature, so ideally there would be almost no ammonia, but we see that in estuaries and coastal systems it can go up to 1.5 millimolar. In aquaculture plants up to 0.3 millimolars, but during algal blooms even higher, or after algal blooms when they decompose. And in aquaculture systems, normally the same range, but if there is an electric failure, for example, of pumps, can go all the way up to 3 millimolar. The Flemish quality guideline is 1 milligram per liter, is about 0.06 millimolar, which is already quite high, and you wouldn't want to keep your fish too long in that, but still often exceeded in some areas in Flanders. So the European Union regularly gives us fines because our nitrogen content in our water is too high. So what happens to aquatic organisms, and more specifically to fish, under high environmental ammonia? Of course, this will prevent any outward flux of ammonia from the fish, which he is producing in his body, and it will induce an inward flux if it is higher than the concentrations in the fish. So this means an increase of ammonia in the body, and therefore the possibility for toxic effects in those fish. Toxic effects that have been seen are ion regulatory disruption, acid-base disbalance, and very importantly, depolarizing neuron cells, leading in severe cases to spasms and death. It causes oxidative stress, and even at lower levels can decrease exercise performance, because it also depolarizes muscle cells, so swimming gets less efficient. If this is a substance that is produced by the fish themselves, and they are likely to encounter in the environment as well, then of course fish would have evolved defensive mechanisms against toxicity of ammonia. And one of the more obvious ways is excrete the ammonia, the one that you produce in your body from your protein metabolism, just excrete it to the environment. Most fish are ammoniotelic, so they excrete it immediately as ammonia, because there's plenty of water around to do so. Although there is some percentage of ureotelism as well. So, synthesizing or producing urea will certainly also help to avoid toxicity. And then you could also convert it back in amino acids. After all, it originates from protein metabolism. So, if we look at ammonia excretion mechanisms, and again I thank Chris for being the author of the original slide, goes or works in many different ways, and there's a nice review by Pat Wright and Chris Wood in 2009, I think it was, about the possible mechanisms and the existence of this ammonia metabolome. The first obvious way is diffusion, and this is very likely an important route, and we still think it's an important route, and this would be easier for ammonia than for ammonium, as this is a charged molecule. It of course depends on the gradient, so there has to be a chemical or an electrical or electrochemical gradient for diffusion to occur by itself. But this is not always the case, that this gradient is beneficial, so there should be other mechanisms. One of the things that helps is that the ammonia diffuses. Ammonia is a gas. It's small, so it can penetrate membranes very easily, and then gets acidified in the outer world, so in the external medium, as it is called here, the water, to ammonium, and then it's harder to diffuse back because now it's a charged ion. So that also keeps the gradient going because now ammonia has disappeared, so there remains a gradient for ammonia. Then you, of course, you need protons. Where can they come from? Well, there could be a proton VATPase that uses energy to transport protons into the water, or an exchange, a sodium proton exchanger. And this would certainly help to produce the charged ammonium and help the diffusion of ammonia. So you see that here, this way, ammonia and sodium transport are linked. But proton ATPase is also associated with sodium transport because it causes an electrical gradient in freshwater fish for sodium absorption through a sodium channel. Finally, there could also be a sodium-ammonium exchanger. Whether or not it was originally a sodium proton exchanger is not important, but as long as it functions. So all of these are linked to sodium transport. This is totally independent of sodium transport. There has been a lot of discussion on whether this is true or not, whether they are tightly linked or not. And it seems to depend not only on the species, the situation, the timing. It is a combination of both, and depending on the situation, just diffusion can be more important, or the sodium linked metabolon can be more important. Lately, however, they also discovered rhesus glycoprotein in the cells, gill cells of fish, and these glycoprotein were first discovered in humans, as for many things. They are called rhesus glycoprotein because they determine the rhesus factor of your blood, and they are now confirmed to be an ammonia channel, where, as I said, ammonium is the predominant form in the cytoplasm, will arrive, the proton will be removed, and it will diffuse as the gas through the channel and then be reprotonized. Oh, I have to go this way. On the other side. So there's different types of rhesus glycoprotein, and we'll talk about a few of them, or I'll talk about a few of them. You have RHAG, which is mainly on the red blood cells, which we did not look at, but RHBG, which is at the basolateral side of the gill cells or the epithelial cells, and RHCG, which is on the apical side. So if we look at the gill epithelium and the transport processes that occur there, then first of all, we have the diffusion of ammonia, which still remains very important. A second pathway is the help or the protonization of the ammonia to ammonium on the other side, and this could be helped by the proton ATPase or by sodium proton exchanger. There could be this direct ammonium sodium exchanger, and then finally also these glycoprotein, which greatly facilitate diffusion of ammonia through these cells. They are now known to respond to many things like feeding, high ammonia exposure, and so on. So, as I said, the presentation is based on chapters of the PhDs of both Amit and Joe. So, we'll go through a few of these chapters. You will see from the color schemes that they are born and raised in India and they like their colors. So, it is a colorful presentation. The first chapter is about the modulation of ammonia fluxes and rhesus glycoprotein, where we looked at comparing different species and tried to look at the ammonia accumulation under high environmental ammonia exposure, and especially also excretion, and how or which underlying mechanisms played a role there. During my years as a postdoc, I did many studies comparing different species, because I'm always wondered why is one species more sensitive to a certain element. I work with metals, with copper a lot, compared to others. So here are the three favorite species. Rainbow trout, who are usually, in this comparison at least, the more sensitive. Common carp, which is a little bit in the middle for sensitivity, and then goldfish, which seems to be able to survive almost everything. So, LC50 values after 4 days is 1.5 millimolar for trout, almost double for common carp, and 9 millimolar for goldfish. So a very clear sensitivity gradient. Amit, in most of his studies, exposed these fish to 1 millimolar of ammonia, so a sublethal concentration for all species. But of course, it would be more severe for. It's always a difficult choice. Do you go for the same concentration for all species, or do you go for the same toxic level, which would be a percentage of the LC50? We have done both, but today we'll mostly talk about the same concentration. So if we expose these fish to high environmental ammonia, you'll see that if we look at ammonia excretion rates going down because it's outwards, nothing much happens with the trout, although they must absorb ammonia from the external medium. They don't seem able to excrete much of that extra ammonia. But in carp, you already see there is an increase in ammonia excretion against the concentration gradient. Let's be clear about that. So the concentrations on the outside are higher than in the fish, and also in the goldfish we see this increased excretion rates. Oh, yeah, so here you see it. If we look at the result in the plasma, so what happens? We see that after a few days you see an extreme increase in rainbow trout. So they are not able to excrete it very well, so they are accumulating it a lot. And this is at least slightly better, or a lot better, in common carp and in goldfish. And you see that it even improves after a week exposure. It's already going down. So they are acclimatizing to this high ammonia. This also had an effect on sodium flux, and this also work done together with Chris. And what we mainly see was an efflux of sodium. So the gills became more permeable for sodium, and they were losing sodium. Certainly immediately, almost immediately here in the trouts, and also in carp and goldfish. But in contrast to trout, again, nothing happens to the uptake, so they're not compensating for what is happening to them. while in common carp we also see an increase in sodium uptake, and the same is true for the goldfish. I always forget they put circles around all these things. So at least these two are attempting to restore sodium homeostasis. And this is a picture that we see a lot also when we look at copper toxicity. For example, metallothionein, the metal binding protein. They're not necessarily higher in the common carp or crucian carp, but they respond much faster to any change. So even though in rainbow trout they might be elevated in the liver, nothing happens when you expose them to copper. They might be lower to start with in crucian carp, but they immediately start synthesizing when new metal is coming in. So it's all about the rates of influxes and effluxes and the response that they have. So we also saw that in trout here on top, the water diffusion through the gills increased greatly, so it means that they had leaky gills under ammonia exposure. And I put this one in because Chris talked about the transepithelial potential last week, and also here we see the biggest changes actually in trout carp and much less in the goldfish. Here you could discuss whether it's beneficial or not, but at least again you see that trout is very much affected. If they lost sodium and they try to compensate, could we see that? Well, you see that in the common carp and the goldfish, indeed sodium potassium ATPase is increased under ammonia exposure and not in the trout. So again, less of a response. So you see it clearly elevated here after a few days to a week in these two species. On the other hand, trout seem to up their proton ATPase, and this also helps with restoring sodium levels, as the proton ATPase is linked to this sodium channel and helps to build the electrical gradient for an influx of sodium. But not so successful because we saw that there was no increase in sodium influx. The goldfish seems to do both. So he's pulling all the strings he can to protect itself against the ammonia. So here and here you see a clear increase. So we talked about these two. They are linked to ammonia excretion, but not directly ammonia excreting. How about the rhesus glycoprotein? What happened there? Well, here we also see differences between the different species, and you see that in common carp and in goldfish. RhCG1 is actually elevated in goldfish from the first point where we measured was after 12 hours up to 1 week. The common carp is a bit slower. It took him a few days to respond, but nothing happened in the rainbow trout. RhCG2, however, did increase in rainbow trout, so it did respond, and also in goldfish, but not in common carp. So each species seemed to have their own response. RhBG, which has a diabetic basolateral side, was only increased in the goldfish. So again, they pull everything they have together to respond to the situation. Where trout activated proton ATPase, the two other ones, sodium ATPase, and goldfish also proton ATPase. So it seems that this one is the most responsive, is also the most resistant. But he has another weapon in his pocket, is that he also increased urea excretion rates. They were pretty low at the start. Excuse me. Always 2 times, I don't know why. So they were again a lot lower as in the 2 other species. As I mentioned, for the metallothionein, it's not about how much you can do, it's about how to respond to a changing situation. So immediately increase in urea transporter expression and also in urea excretion rates. So it can also convert ammonia to extra urea and get rid of it like that. So to conclude, we see that basically we see that common carp and goldfish respond the best of the 3 species, and goldfish really can activate all the different processes they need to deal with ammonia challenge, which is extra bonus of urea synthesis and excretion rate. So they seem to be better adapted. So then Amit also said, well, gill damage is one of the common processes in or symptoms of ammonia exposure. Did something happen at the gills, and are they responding better there as well? So the gills, of course, consist of gill arches and gill filaments and lamellae, where the water and the ammonia will run through. And if you look at it under an electron microscope, it looks like this. And you can focus even closer on the lamellae. And we will be mainly looking at 2 things: the thickness of the filament and the thickness of the lamellae. And there are also the mitochondria-rich cells, where you find most of these transporters we just talked about, and pavement cells, which are the largest area of surface in these fish. And if you look on the surface, then you see the pavement cells as the larger surface, and the little holes are where you can find the mitochondria-rich cells. So these are these crypts here at the top. So gill remodeling is something that has been talked about last week as well. That has been discovered that gills are not a static anatomical feature, but they can be very dynamic, and some species really change their gill structure according to the situation. So the question was, can these species do that as well? We know that goldfish can do it under hypoxia and under temperature stress. So will this also play a role in this ammonia for us? Again, our same 3 species, our same level of exposure. This is what control gills look like, so all quite similar. Perhaps here you could say that the trouts start off with a little wider filaments with shorter lamellae, while the goldfish had quite pronounced lamellae and the common carp. This is because we were at relatively warm temperatures, because at cold temperatures they would have very short lamellae. As you know, metabolism is slow, they don't need much oxygen then. After exposure in the in the rainbow trout, we see very little change. Perhaps a little bit of swelling of the lamellae, certainly at the tips. So again, this is a sublethal concentration, so the damage is not used. On the carp, you could see not only that the lamellae are maybe a bit thicker, but also the filament is clearly enlarged compared to here. And we actually think that reducing the surface might aid to prevent ammonia influx. So it helps to avoid the influx of too much ammonia. And this has been taken to the extreme with the goldfish. We know they can do it under hypoxia and at cold temperatures, well, also under ammonia exposure, they try to reduce the surface as much as possible to reduce the influx of ammonia. And at some of the tips it was extreme. You couldn't see any lamellae at all. It was just a smooth filament with maybe some small remnants of lamellae there. So here we see that in these larger structural studies that in trout there's very little response and maybe a little bit of thickening of lamellae, which also increases the blood water diffusion barrier, but this is really pronounced again in the goldfish. It could also cut down the cost of iron regulation or prevent too much sodium loss if this is caused by too high concentrations of ammonia. If we look at the different cells, then in common carp and the goldfish we see kind of a similar structure where you have the mitochondria rich cells here with the microvilli, and here as well, and then mucus cells as well with the white pointed arrows. And in the trout it looks quite similar as well. Again, you see the mitochondria rich cells at different spots and then a mucus cell there. But when we expose, we see a different picture. If we expose them to high environmental ammonia, you see that the mitochondria rich cells enlarge. So they have more exchange surface with the water. While in common carp, we actually see that they get smaller. See very small surfaces, and the microvilli seem to disappear a little bit, again reducing the contact. The empty craters you see here are mucus cells that have released their mucus. And again, extremer in the goldfish, even in the pavement cells, you see that micro ridges disappear, reducing the exchange surface with the water. Lots of mucus going on as a protection, and the mitochondria rich cells seem to almost disappear in the surface. So clearly here the mitochondria rich cells are closed off, trying to prevent loss and entrance, or loss of sodium and entrance of ammonia, while the trout seem to have an opposite response. They go in overdrive as they respond to many things, and also here is less indication of loss of micro ridges, although they change in shape, and also less production of obvious production of mucus. If you look in light microscopy, you can see this interlamellar cell mass here. It is present in the trout as well, but it is, even under normal circumstances, more pronounced in carp and in goldfish, which is why the filaments look thicker. And under ammonia exposure, nothing much happened, as we saw in trout, but we see an increase in this mass in the common carp and in the goldfish, even with mitochondria rich cells and mucus cells on top of the mass. So insignificant gill remodeling in the trout, extreme gill remodeling in the goldfish. Then in the last study from Amit, they also put extra stressors on top of the ammonia and wanted to look at how would they deal with this stress in real life when they had to swim, maybe not find food. So we looked at different feeding regimes and at exercise. So natural stressors, on the one hand you had ammonia, restriction of food, so starvation or fasting, I should say, and exercise. So we aim to see whether this changes their metabolic and physiological responses, and the iron regulatory responses and hormonal control. This study was only done, or the work I'm going to present was only done on goldfish. We also did this on common carp. So the fish were either sampled after routine swimming, just normal swimming around in the tank, or after exhaustive exercise, and we'll only call that exercise in this presentation. This time they were exposed to much lower concentration, our Flemish water quality guideline, and this is certainly very sublethal, so about more than 10 times lower than as what you saw before. And then we had fish that were either fed, and there we had control fish, of course, and ammonia exposed fish, exercised and non-exercised, and the same for fasted fish. I always tend to always have this, oh, why don't we look at this and why don't we look at that? And then statistics become really a horror if you have to compare everything. But anyway, so we sampled and we looked through time as well as another variable. Here's what you get. Ammonia excretion rate actually was, as you would expect, larger in the fed fish because they are metabolizing much more. It's not always significant, but it's very systematical. It's larger, it's bigger everywhere. And after a few days, like after 4 days to 3 weeks, this effect was most pronounced. Possibly here there was still food in the stomach, in the intestines of the fasted fish. But then if you exercise them, the first thing, so even in control fish you see that the excretion rate is higher. If you exercise them, it almost doubles. And you have 1.5 micromole per gram per hour here, and over 3 micromole per gram per hour in the exercise fish. Normal, they're metabolically much more active. But you also see that the difference between the fed and the fasted fish becomes much more pronounced and is now significant overall. Not only significant between the control and between the fed and the fasted fish, but also between the exercised and the non-exercised fish, and then also on starting value. So much more pronounced here, everything is increasing. What with plasma ammonia concentration? Are these feeding fish very metabolically active, having higher plasma ammonia levels as they are digesting food? Well, surprisingly, no. It are the fasted fish that have the higher ammonia level. So they, not in the control, but as fasting continues, you see that they start to have higher ammonia levels. So the excretion rate is reduced, but it's not because the concentration gradient is not there. Because they actually have higher ammonia in the plasma. They just don't seem to be able to get rid of it anymore. And again, everything is more pronounced in the exercised fish. This high plasma ammonia has the classical effect on swimming capacity. Muscle cells depolarize, is probably most probably the cause, and you see that their critical swimming critical swimming speed is reduced, especially again in the starved fish that have the increased plasma ammonia. You So if plasma ammonia goes up, swimming performance goes down. We also saw increased plasma lactate, which might also explain the reduced swimming performance. So anaerobic metabolism seems to be stimulated in all the groups. So also in the fat groups we saw lactate accumulation and depletion of energy stores. So they didn't like the chronic ammonia exposure very much. But if you then exercise them, then you see that these effects get much worse. So to our surprise, this effect was larger on the fasted fish, because you would expect they're not so active, they would have less response. This was also done in common carp, and there we saw more or less the same, but with a little bit of delay. So again, the goldfish respond faster. So this is all more about toxic effects. So the question is, can we also use this science? Can we do something with it except just see what happens? So this is more Jo's work. She again looked at ammonia under exposure of high environmental ammonia, and she looked at it in common carp, both just exposure to high ammonia, also looked at fasting and at exercise, but in different experiments. And then in another part of her PhD, what I'm not going to talk about, she also looked at effects of ocean acidification on acid-base regulation in general and ammonia transport in more in detail. So common carp for these top studies, which I'm going to present, and then she worked with European sea bass and with spotted redfish for ocean acidification work. First thing she did is think about whether pre-exposure to very low levels of ammonia could actually help the fish to deal with high ammonia exposure. So, it has been known that sometimes pre-acclimation or pre-exposure to a certain substance or situation can improve your reaction afterwards. You're kind of primed, and they also call it a stress memory. You remember how to respond. This is certainly true for metal exposures, where you can have an induction of metallothionein, for example, or extra sodium potassium ATP is being synthesized. So then when it gets worse, you are already prepared. So we've seen this also in other species. For example, in these species, when they were exposed to hypoxia, they are also primed to respond better to more severe hypoxia afterwards. We see it in salinity exposures as well, where a first exposure to a low level of the stress, and then the stress disappears for a while, but then when they're re-exposed, they respond much better. So that's what we wanted to do. Is pre-acclimation to ammonia also possible? And if so, what are the mechanisms behind it? So Jo also worked with common carp, and she exposed them to more or less 10% of their LC50 for different periods of time. So 3 days, 7 days, and 2 weeks. Then, of course, she had these ammonia pre-exposed. She also had control fish. First thing she did was look at survival at high ammonia exposure, and to do that, she took the values actually extremely high to be able to look at survival at the LC50 value. And then secondly, first the results. And then she saw that indeed, after 3 days and 7 days of pre-exposure to low levels of ammonia, the survival improved in these fish. But strangely, after 2 weeks, this result had disappeared. No more improved survival. Then she exposed them again, this pre-exposure to the low levels, and then exposure to a slightly higher level, like half of the LC50 value, and she looked at sublethal endpoints after 12 hours and 2 days, and looked at ammonia excretion dynamics. So without pre-exposure, if you look at ammonia excretion rates, there is an excretion outwards. And this, in the control condition, nothing much changed because it's always the same condition. If you then expose these fish to the 1.35 millimolar, what you see is that you get an influx. The ammonia concentration increases in the water, the gradient reverses, so the ammonia fluxes into these animals. And yeah, this is the same all the time because nothing really happened to these controls, right? So it's just a consistent response. But then, if you look at the fish that were pre-exposed, you actually see that from the start there is a real increase in excretion rate. So no uptake. They can excrete against the concentration gradient, and they can even increase this excretion against the concentration rate. At least that is true again at 3 days, where it's significantly different with the top, but here at 7 days it's significantly different with their own control, just pre-exposed, and the high levels. Again, after 2 weeks, surprisingly, they seem to have lost this capacity, and there is again an influx, even though it's still smaller than in the unexposed fish. So, fish pre-exposed to ammonia for 3 and 7 days facilitate efficient ammonia excretion. So she looked at the different transporters or at the rhesus glycoprotein that could be involved, and this is RHCJ, so this is the one here on the apical membrane without pre-exposure. This is the basal expression rate. After 12 hours, no response. After 2 days, they do respond. They do see an increase in their rhesus glycoprotein synthesis probably. This is just gene expression, but you can assume that the protein is also synthesized after that. But not yet enough to reverse the ammonia influx, because we saw that remained the same. In the pre-exposed fish, you see immediately, as soon as after 3 days, there is already an increased gene expression. The same is true after 7 days, and it's still true after 2 weeks, although again it's not better anymore than in the unexposed fish. So something has happened. So again, 3 and 7 days seem to be good points for pre-acclimation. Here she looks at RHCB, so another isoform of the glycoprotein. And again, in pre-exposed fish, you see that at least at 7 days, this is increased in the carp. RHBJ, so here on this side of the cell, nothing much happens. We also saw in amid studies that only in the goldfish they were induced as well. So nothing happens here. And then she also looked at the sodium proton exchanger, and again we see higher levels of expression in these pre-acclimated fish, so this could also help the fish here. So overall, we see after 3 days upregulations in different exchangers, but after 2 weeks only in sodium potassium ATPase. There was nothing changed in proton ATPase. Remember, when we compared the 3 species, only the trout had an increase in the proton ATPase. So big upregulation here, and that also meant survival for these fish and increased ammonia excretion. So yes, they can develop this stress memory, but it is not until the end of times, and it wears off after a few weeks, so they seem to become kind of or the system seems to be overloaded. There must be a negative feedback control for the system. Yes, she's working also towards aquaculture, so it could actually be useful to prime your fish before transport with a little bit of low ammonia, in case that there is ammonia increase, that it's not so damaging for the fish. Another practice that happens in aquaculture is that you fast your fish a few days before you put them into transport. This is because you want to keep the water quality okay. So when the fish are fasted, they should use less oxygen and also produce less ammonia, which keeps the water quality better during transport. Very often this is a standard period, like 2 days, but you could also look at it more into detail and see what is actually the best period. So this is kind of the situation and the stress during transport. Ideally, this is all in well aerated containers, but in practice it could also be this situation where fish even heat up during transport. So you want to lower metabolism as much as possible, but we don't want to get in that effect that Amit saw, where after a longer time of fasting, you see that the capacity to excrete ammonia disappeared, and ammonia transporters were down-regulated because they had nothing to do, basically. So we want to look really for the ideal fasting period where the metabolism is down, but other processes are not affected, and the response, the fish is still able to respond to changes. So she looked at different responses again. Oxygen consumption, ammonia excretion, obviously, ammonia in the plasma, ions, energy stores, because this is of course very important in aquaculture. You don't want your fish to lose weight, and then also at gene expression of these transporters. So again, fasting with food, without food, and she followed them over time. What we see in oxygen consumption rate is indeed there is a drop in oxygen consumption rate. We first saw a little increase after 2 days. Maybe the fish are looking more actively for food, but then after that, in general, you see a reduction in oxygen consumption rate. It doesn't seem like much, but 15% reduction can mean survival or not during a transport. So the trend is there to reduce the energy metabolism. You don't necessarily have to wait very long because it just drops to a certain level and then remains more or less stable. If we look at ammonia excretion, the trend keeps going on over time, so it drops more and more and more. And it becomes significant from day 6 onwards only. So this was kind of a surprise, although you can see that it starts to drop earlier as well. And then if we looked at plasma ammonia, very good plasma ammonia levels here after 2 to 6 days of fasting. So the excretion was not reduced that much, but the production must have already slowed down. But then after that, the beneficial effects seem to wear off a little bit. But the water quality would still be good because there is no excretion. But inside the fish it's higher, so that doesn't really help. So she looked at different tissues and at the ammonia transporters. You don't want a reduction in these because you want the fish to be able to respond in case the ammonia does increase in these bags sitting out there in the sun. And what we saw, again, nothing significant in RHBG, but it seems to be more due to variation. But from day 8 to 10 onwards, we see expression drops in RHCG. We want to avoid that, so we will stay away from these long fasting periods. They're not beneficial anymore. Plasma ions is a bit wobbly. Seems to be a drop in the beginning in sodium and chloride content, but then it seems to repair itself, so they seem able to increase their uptake through the gills. Then it must be because they don't get any food. Potassium is a little bit irregular, so nothing alarming here. You know, if you fast them long, they can compensate, and they do this by increasing the sodium proton exchanger and by increasing the sodium potassium ATPase, although this was less pronounced. So we're not going to panic about ions in fasting fish. Mm-hmm. What we want to avoid is this happening. And lipid content, glycogen content, and certainly protein content. You want your fillet to be nutritious, and you want a large fillet basically on each fish. So certainly no longer fast. 8 days was a limit also for the RHCB expression. So or RHCG expression. So we want to avoid these longer exposure periods. So in conclusion, here you can say that oxygen consumption was the first to start to drop, and then you had ammonia excretion rates that dropped, but still maintaining RHCG expression, which is good. And then in the longer run, you got a worse effect. So we think that 4 to 6 days is actually a better starting period or fasting period than the 2 days. Let's say this is carp, right? We don't want to generalize to all species immediately, but you could at least look at it if it's not better to fast them a little bit longer. They're not losing weight yet, so this should not be a problem. And the final one is where we actually swam carp. This is also thought to be a possible way to increase growth in fish. If you exercise them a bit, they will not only have stronger muscles, but they will actually increase their growth rate, even if you give them the same amount of food. Probably because food conversion is improved. And it's also said if you swim them at a low speed, ammonia excretion is easier. We saw if you swim them at exhaustive speeds, then you get increased ammonia in the plasma, but at a low speed, this could be beneficial. So we put little carp in these raceways that we have in our mesodrome and let them swim for a month. They were little ones, 1.5. What was it? 1.5 centimeter, more or less. 6.4 centimeters, sorry, and then we have swum them at 1.5 body length and 2.5 body length. We couldn't measure oxygen consumption in here. We tried to do it on the whole school, but they were really too small. We had hoped that they would have been a little bit bigger on arrival. But then we put them in separate Blaska spirometers and followed oxygen consumption and ammonia excretion rates there, and looked at general performance. Did it work? Because first of all, nobody ever done it with carp. Yes, at 2.5 body length you see a clear increase in weight gain over the weeks. They didn't lose weight here in between these two. We just took a subsample of fish, and this is what we got. So a clear beneficial effect for growth. If you look at specific growth rate, then it's also increased. So this is what we wanted to see. Why do they increase their growth rates? Well, we think it's partly hormonal, so we looked at the expression of some hormonal receptor, and we see that the growth hormone receptor is certainly induced in these swimming fish. And also the insulin growth factor is induced in these fish. So exercise promotes this hormonal processes or pathways. To our, well, not to our surprise, but we also noticed it took a long time, but at the end they had lower water muscle content, which is good because you have a firmer fillet, and if there's less water, it's more protein. But that took a surprisingly long time. To our surprise, there was not much difference in oxygen consumption swam at the same speed. So now they were in small respirometers, we put them at the standard speed. So there was no training effect. You would expect that the fish that were used to swimming would reduce their oxygen consumption if they have to swim at a lower speed. But no, nothing much to see there. And also they didn't improve their swimming performance. The eucrits stayed the same. Ammonia expectorate was largely increased at the 2 swimming speeds. So this is a beneficial effect of the swimming. And despite the fact that their metabolism or protein metabolism must have been higher with a higher growth, we didn't see this in the plasma because they were excreting very efficiently. So yes, the swimming did help to increase growth in this these fish, and it seemed to be a bit more beneficial food conversion because they got the same amount of food, all of them. Hormonal effects, very important. The growth hormone pathway was stimulated, and it certainly didn't hurt that ammonia excretion was well increased or easier in these swimming fish. So overall, we did see that pre-acclimation can be beneficial, but there is a negative feedback after a prolonged time of exposure. The fasting, maybe 2 days is not long enough, or maybe it could even be better if you fasted them a little bit longer, but not longer than a week, because then we start to see these negative effects. And yes, also swimming could induce growth improvement in common carp. Common carp doesn't seem such an attractive fish as a salmon, for example, for consumption, but actually it's the second most produced freshwater fish in aquaculture, and it's very popular in Eastern Europe, Asia, some of the Arabic countries as well. So at the Aquaculture Society, they were actually quite enthusiastic about this, and Joe won several prizes in from the World Aquaculture Society, both in 18 and in 19. So that's nice. If you have to defend your PhD, you can have this show. So finally, I would like to thank everybody in Sphere for all the help. The University Research Board funded Joe's PhD, and the Science Foundations of Flanders funded Amit's PhD and postdoc. I want to thank Chris for all the collaborations, and ideas. Some of this work was when he was visiting our lab. And then finally, life is also more than just work. So to show that I also do other things, although the basketball is a while ago, just comes back.